It was a memorable holiday season in 1968 as astronauts Borman, Lovell, and Anders became the first men to leave the Earth and orbit the Moon, the first to see its hidden side. The Apollo 8 mission marked the culmination of the first 10 years of NASA's formal existence, a decade of accomplishment in what NASA Administrator Thomas Paine has called man's new domain of life. And 1969 saw man reach his historic goal, Apollo 11's first manned landing on the Moon, the first small step of Neil Armstrong. And with Apollo 12, the first 4 lunar surface explorers. By the end of 1969, the American manned spaceflight program had accomplished the 6 one-man suborbital and Earth orbital flights of Mercury, the 10 two-man Earth orbital missions of Gemini, and the first 6 three-man Apollo missions. And behind these headlines, there had been thousands of spaceflight systems tests on the ground, as well as unmanned flight tests. The manned spaceflight program is the successful product of the energies of hundreds of thousands of men and women working directly in the program, in government, universities, and industry. The lunar landing demonstrated that 300,000 people could work closely together to achieve success. It was the achievement of scientists and engineers, executives and administrators, technicians and pilots, statesmen, lawmakers, and John Q. Public. Of key importance to the success of the space program have been groups of industry executives and government administrators who have worked together in teams. Also, NASA has depended heavily on the Science and Technology Advisory Committee and on specialists from headquarters and from the 3 field centers at Houston, Huntsville, and the Kennedy Space Center. The Science and Technology Advisory Committee in 1969 outlined recommendations for future space programs. These studies were invaluable to NASA in preparing a report on future space activities for the President's Space Task Group, which was charged with responsibility for preparing a definitive recommendation on the direction the United States space program should take in the post-Apollo period. It was a formidable task when one considers the accomplishments to date, which will serve as a foundation for the future, the wealth and trained men, facilities, and equipment to be utilized if possible, and at the same time the demands upon the national economy from so many other worthwhile areas of social promise. How, then, can the United States take full advantage of its preeminence in space and still remain within reasonable budgetary limits? In his 1970 policy statement on the space program, President Nixon outlined 3 general purposes: exploration, scientific knowledge, and third, turning the lessons we learn in space to the early benefit of life on Earth. With these 3 general purposes in mind, let us preview some of the highlights of future space activities. To take full advantage of existing capabilities, the exploration of the Moon is continuing. Beginning in 1970, landing sites selected for Apollo missions were varied and quite different from Apollo 11's Sea of Tranquility or Apollo 12's Ocean of Storms. Target areas have included the hilly uplands near the crater Fra Mauro and other mountains, rills, and craters believed by scientists to be most rewarding for geological and geophysical studies. A launch rate of 2 per year was set as an economical minimum to permit maximum responsiveness to new scientific discoveries while maintaining mission safety and efficient utilization of support personnel. In addition to exploring and sampling near the landing sites, an important goal of continuing expeditions to the Moon is the establishment of new scientific instrument stations at a variety of sites. These augment experiments and instruments already installed on the moon and provide an expanding network for the maximum return of scientific data. Additional stations with seismometers, for example, make possible more complete analyses of the structure of the moon's interior and enable scientists to determine if moonquakes or volcanic activity might still be taking place on the lunar surface. Present NASA schedules continue a series of Apollo lunar landing missions, which began with Apollo 11 in 1969. The missions are similar to one another, but with different sites and with gradually increasing capabilities. Many experiments are new on each mission. For example, the use of a lunar drill for penetrating several feet below the surface, and the creation of a man-made moonquake by crashing the Saturn third stage into the moon, and recording the shock waves as on the aborted Apollo 13 mission. Later plans call for extended Apollo missions with longer surface exploration periods and such aids to extended coverage as a lunar roving vehicle similar to this early mock-up. Such extended Apollo capability results from only minor modifications to the spacecraft. Another manned spaceflight program of the early 1970s consists of the launch and operation of a manned Earth-orbiting workshop, forerunner to permanent space stations. The workshop is the basis of the Apollo Applications Program called Skylab. It uses pre-existing Apollo facilities, personnel, and hardware. A converted Saturn V third-stage tank makes up the workshop proper, equipped and furnished on the ground as a two-story mobile home and laboratory with about as much living and working room as a three-bedroom house. Supporting modules attached to the workshop are the airlock containing communications, electrical power, and environmental control systems, and the multiple docking adapter which serves as a berth for visiting spacecraft. The third module attached to the workshop is the Apollo telescope mount, one of the major experiments of the program. The complete assembly is placed in near-Earth orbit by the first two stages of an already allocated Saturn V vehicle. A day later, a three-man crew is launched into orbit by a smaller Saturn 1B vehicle, one of 7 in reserve, due to the early success of that vehicle's flight test program. After attaining orbital flight, the crew rendezvous and dock their Apollo spacecraft with the orbiting workshop. Separate crews of 3 men each man the workshop. The first crew spending about 4 weeks, then returning to Earth, and the next crews remaining in orbit for as long as 8 weeks. Skylab is designed to provide experience and data on the ability of men to live and work in space for extended periods, in far more spacious quarters than the Apollo command module. The workshop can increase our knowledge and applications of multi-band terrain photography, including infrared. Improvements in instrumentation can result in better sensors for automated spacecraft. Substantial benefits to living conditions on Earth are promised from mapping, from surveys of mineral, agricultural, and ocean resources, and from measurements and remedies developed to reduce pollution in the Earth's air and water. As a forerunner to permanent factories in space, Skylab scientists and engineers are able to investigate processes such as electron beam welding and metal joining. Similar experiments were conducted by the Soviet Union in 3 Soyuz flights in October 1969. We can also experiment with other techniques, taking advantage of previously unavailable space conditions, such as almost total vacuum and zero gravity, which someday may lead to the growth and fabrication of crystals in space and the formation of new materials hitherto unknown. Finally, the workshop makes possible another milestone in man's search for answers from the stars. Its attached Apollo telescope mount supports astronomical telescopes through which men in space can study the sun, unhampered by the distortion and shortwave screening effects of the Earth's atmosphere. These experiments supplement and round out data from NASA's unmanned orbiting astronomical observatories. The workshop's observatory has 6 telescope systems for observing, measuring, and recording the complete spectrum of the sun's radiation, providing man with a more intimate knowledge of this source of energy and life. To reduce the cost of spaceflight most drastically, a 2-stage reusable space shuttle is under study. Difficult design problems of weight, aerodynamics, and re-entry heating are being overcome. Their complexity can be seen from a description of the shuttle's operational profile. It will be launched vertically by the rocket engines of its first stage, the booster element. It will attain a speed of several thousand miles per hour, about 40 miles up. The first stage will then peel off, and its pilots will fly it back to Earth for a horizontal aircraft-type landing on a conventional runway. After the first stage has separated, the shuttle's second stage engines will be ignited. Streaking through and beyond the thin upper atmosphere, this orbit element will accelerate to the nearly 18,000 mile per hour velocity necessary to achieve orbital flight, to deliver its payload and perform its mission. Later, the second stage and its crew also can re-enter and land at an airport with its return cargo. The space shuttle will be built for at least 100 round-trip flights with minimum maintenance. The reusable shuttle program is a good example of cooperation between NASA and the Department of Defense. The shuttle is being designed by NASA to meet the requirements of the two agencies. Also, with the shuttle for transport, technicians will be able to reach automated satellites and probes to repair, maintain, refuel, and refurbish them, or to reposition or retrieve them for return to Earth. With its maneuvering ability and its capacity for adding passengers, the shuttle also has a valuable potential as the first space rescue vehicle. By combining the space shuttle with an orbiting space station, a greater integration of manned and unmanned scientific missions will be possible. The primary purpose of the shuttle is to rotate crews and replenish supplies for the space station. The decks of the planned station will provide permanent working and living facilities for 12 men. Living conditions will be comfortable and attractive, with private staterooms, showers, recreation areas, kitchen and dining room, as well as work areas. The station is a self-contained scientific laboratory and experiment facility where Earth-oriented applications can be conducted and where scientific and technological research and astronomical observations can be performed for the further benefit of mankind. It is similar to a highly flexible, multidisciplinary research, development, and operations center on Earth. Astronomy, physics, chemistry, and the life sciences will flourish, as will materials research and manufacturing. The station will be a focal point for productive international cooperation and joint ventures that will include foreign nationals as members of the onboard team. The space station will stimulate technology and will foster economies by combining many functions at a single permanent location in space with efficient resupply and crew transfer operations. It will have an operating life of at least 10 years. Several other space developments are technologically feasible today and seem socially and economically valuable for tomorrow, now that man has begun to live and work in this new domain. As resources become available in the years to come, outer space programs may be extended. Some of the concepts now under study include a reusable nuclear shuttle based on a Nerva nuclear engine for use between Earth and Moon orbits and for propulsion on interplanetary missions. A space tug for inter-orbit transport with similar commonality and versatility. A very large Earth-orbiting space base, an island satellite for perhaps 100 scientists and technicians. And as a later goal for our rapidly accelerating century and millennium, to quote the President once again, we will eventually send men to explore the planet Mars. Where then, as we survey the future, do we stand now? What can we do that we could not do just a few short years ago? We stand now on the very edge of space, newcomers trying our new skills. We have lived in space and can survive there for at least 2 weeks at a time. We can rendezvous and join spaceships together during flight, and we can perform useful work in the strange, unsheltered space environment. We can walk upon the moon, explore its ancient terrain, erect experiments and miniature power stations. We can gather specimens for the clues they'll give us back in Earth laboratories. Scientific clues revealing facts about the origin and the history of the moon, the Earth, the sun, the solar system. With space-borne sensors, manned and unmanned, we can see the Earth itself more grandly, can see the forest and the trees, can study rivers, oceans, deserts. We will learn how to prospect on a giant scale for oil, minerals, underground sources of fresh water. We can look down upon the clouds and winds and rains of Earth and determine how to forecast their formation, and even how to alter and control them. We can improve the navigation of our ships and aircraft. We can measure ultraviolet, infrared, and all known wavelengths of radiant energy with unmanned instruments above the clouds. Soon we'll have men at telescopes and scientific laboratories in space, with man's greater versatility and competence. And soon, men in space will be able to conduct materials research and technology in the unique, weightless vacuum conditions available to orbital flight. We have done many things that are new after little more than a decade of spaceflight, and we are on the threshold of many more. Presently, we are cooperating in space with many other nations. In the years to come, our space program will offer increasing opportunities for participation by other countries. Space science developments will benefit people everywhere by activities ranging from observations of our environment to worldwide radio and television, benefiting commerce and education. And as a nation, the United States will continue to build on the confidence and national security that comes with preeminence in space technology and the admiration of people throughout the world.